Hello chemists, this is Ms. Placino and you are watching a tutorial on dimensional analysis. In this video we're going to cover what dimensional analysis is. We're going to look at some general applications of dimensional analysis, and since this is a chemistry course we're going to look at dimensional analysis in regards to three specific topics: mole conversion, solution chemistry, and stoichiometry. Let's get started. All dimensional analysis is a technique that is used to convert between units. And the way we're going to make these conversions is by using fractions that are equivalent to 1. So let's look at a couple examples. You know that there are 100 centimeters in a meter. So it's the same exact distance, it's just expressing that distance using two different units. I can set up a fraction that's equivalent to 1 because the numerator and denominator are the same exact distance, either by writing 100 centimeters over 1 meter, or 1 meter over 100 centimeters. Again, they're equivalent to 1 because it's the same distance in both the numerator and denominator. Another example, you know that there are 24 hours in one day, same duration of time, two different units. So you can probably imagine that I can set up two equivalent fractions, 24 hours over 1 day, or 1 day over 24 hours. You might be wondering how you're supposed to set up these fractions when you're actually performing dimensional analysis, and let's look at some examples of that. So the way we're going to use these fractions that are equivalent to 1, and we'll call them conversion factors, is to work stepwise and cancel out unwanted units. So let's say that you want to figure out how many seconds are in 17 years and you don't have access to Google. I will do this the old school way with calculations. So really what you want to do anytime you're doing dimensional analysis is start off just by writing the information you're given, so usually a number and units. I'm going to put it over 1 just to help me keep all my conversion factors organized. I have no idea how many seconds there are in a year, but I know how many days there are in a year. So I'm going to multiply 17 times 365 days over 1 year. 365 days in 1 year are the same duration of time, they're just two different units. And I chose to set up the fraction this way so that I could get years to cancel out. Because years is in the numerator in one term and then in the denominator in another term, it will cancel. If I flip my fraction upside down and I make it 1 year over 365 days, I would end up with the units years squared over days, which really isn't a thing. I'm going to keep repeating this and use conversion factors to get closer to seconds. So I don't know how many seconds are in a day, but I do know that there are 24 hours in a day. I can cancel out my days. I know that there are 60 minutes in 1 hour. That'll allow me to cancel out my hours. And finally, I know that there are 60 seconds in a minute. I can cancel out my minutes. I'm left with seconds. That's what the question is asking me about. That's the unit I've got. That's usually a pretty good signal that you are done with coming up with conversion factors and you're ready just to calculate. So hopefully no surprise, you end up with a ton of seconds. We've got to look at significant figures. I see 2 sig figs and the number 17. And then if you think about it, these 4 conversion factors are definitions, so they are correct to an infinite number of significant figures. So I've got to take this gigantic number and trim it down to just 2 sig figs. And I end up with roughly 5.4 times 10 to the 8th seconds. Pause the video, take a moment and try out these practice problems. All right, if you've got 32.5 ounces, and you can use the little conversion factors that are on your sheet, you can probably figure out that that's 9.22 times 10 to the 4th centigrams. And again, it's all about making the units that you don't want cancel out, and eventually getting to the units that you do want in the right location. In this case, I need centigrams in the numerator. Question number 2 is a little bit more complicated, 65 miles per hour into meters per second. I've got really 2 different types of conversions to make, a distance and a time, but it's the same exact idea. Work stepwise, get the information or the units that you don't need to cancel out, get the units that you do need in the right location. So I need meters over second, and that's what I end up with, meters over second. And finally, the last one, even more complicated, 13.6 grams per milliliter. Convert that into pounds per cubic foot. Get rid of the units you don't want. This one is a little bit tricky because we've got cubic centimeters here. So instead of just multiplying by 2.54 centimeters over an inch, you've got to cube that term. You've got to cube the 12 inches equals a foot term as well. But ultimately you can get to roughly 848 pounds per cubic foot. Most of the conversions that we're going to look at this semester are going to fall in one of these two categories. Nothing usually too tricky with the exponents. So let's look at some specific, or I should say chemistry-specific conversions, including mole conversions. Hopefully you remember that you can express mole in a variety of ways. For example, 1 mole is equal to 6.02 times 10 to the 23rd particles. If you've got a mole of gas at standard temperature and pressure, it has a volume of 22.4 liters. And if you have 1 mole of a pure substance, it's going to have it will have the mass in grams of that substance. So let's say we're looking at CO2. If I have a mole of CO2, I have 6.02 times 10 to the 23rd particles of CO2, or molecules of CO2. I can set up those fractions with 6.02 times 10 to the 23rd in the numerator or the denominator. I would have 22.4 liters of carbon dioxide at standard temperature and pressure. That would be 1 mole. Again, I can flip that upside down as well. And finally, it has a molar mass of roughly 44 grams. So if I have 44 grams of carbon dioxide, I have a mole of carbon dioxide, regardless of how I orient it. And it turns out this molar mass conversion is going to be the most useful one this semester. This is kind of a fun trivia fact. This would be nice if we got to work with gases more often, but unfortunately we don't. So a lot of it's going to be molar mass conversions. Let's try one out. So let's say you've got 4.5 grams of potassium thiocyanate, and you need to know how many moles that is. Just to quickly review, to find the molar mass of something like KSCN, you need to add up the masses of those 4 elements. So potassium's mass is roughly 39 grams, sulfur is about 32, carbon is 12, nitrogen 14. And you can do the math and you can figure out how many grams per mole the molar mass of potassium thiocyanate is. I would recommend for this course just Googling the molar mass. You don't want to be limited to just 2 significant figures because of your molar mass calculation. So just look it up and you can get a whole lot more places after the decimal point. But it's the same idea. Get the units you don't want to cancel out, and it'll leave you with the units you are interested in if you set everything up correctly. Pause the video, try out questions 2, 3, and 4. All right, question number 2 is very similar to question number 1. You've got a mass in grams, use the molar mass of sucrose, and you can get to the number of moles. We're going in the opposite direction for questions 3 and 4. You need the molar mass of potassium hydroxide, but it's a very similar calculation. This time get your moles to cancel out, and you're left with an answer in grams. And if you've got magnesium sulfate, heptahydrate, and 1.7 moles of it, you're going to have a massive amount of that compound, 419 grams. Again, they all have the same thing in common. Cancel out the units you don't want, and you're left with the units you do. Solution chemistry is something that is extremely important. Almost every lab we do this semester, you're going to be making a solution to a specific concentration, so this is really a crucial skill. Hopefully you remember from earlier chemistry classes that usually when we're talking about concentration, we're going to express it in terms of molarity, which is moles per liter. So let's say that you need to find the molarity of a solution prepared by dissolving 2.57 grams of Na2S, sodium sulfide, in enough water to make 100 milliliters of solution. Well, I've got grams and I've got milliliters, and I ultimately need to get to moles and liters. So if I use the molar mass of sodium sulfide, which would be, 23 times 2 for the sodium, plus 32 for the sulfur, I should be able to come up with my molar mass and convert it to moles, and I can very readily convert milliliters into liters. So I've got my 2.57 grams of sodium sulfide. Sodium sulfide has a molar mass of just about 78 grams per mole. Grams will cancel out, and I'm left with moles, and it's in the numerator, so this is off to a good start. I need moles per volume, specifically moles per liter. So I'm going to take the information I've got, 100 milliliters, and I'm going to put it in the denominator. I can convert out of milliliters into liters using the conversion factor, 1,000 milliliters equal a liter. Milliliters cancel out. Now I have moles over liter, or moles per liter, and that's exactly what I need for molarity. So if I prepped a solution in the manner described in the question, I'd have a 0.329 molar solution of sodium sulfide. Pause the video, try these questions out. Question 1, very similar to the question we went over together. I've condensed it down a little bit. I've taken my 250 milliliters and immediately converted it to liters, or I should say directly converted it to liters without showing the step. That's completely fine. You're welcome to do the same. I end up with moles per liter. We're going in the opposite direction for questions 2 and 3. This is more of a theoretical calculation. So this is, before you can run your experiment, you need 50 milliliters of a 0.5 molar solution of sodium chloride. How would you prepare it? In other words, how many grams of sodium chloride are needed? Same general idea. You know the molarity, get your moles to cancel out, give you grams. 50 milliliters. I can use the 1 liter equals 1,000 milliliters conversion to get rid of both the milliliters and the liters, and I'm left with an answer in grams, 1.46 grams. Question 3, very similar to question 2. I've condensed it down again. I've converted directly without showing the work from 100 milliliters into 0.1 liters. But as you probably would imagine, everything cancels out again, and I'm left with a unit of grams, which is what I'm looking for. Finally, we're going to do a lot of dimensional analysis when it comes to stoichiometry. So stoichiometry is really just the math of a balanced chemical equation. So whenever you've got a question that seems like it's going to involve stoichiometry, if it hasn't been done for you, you need to go through and balance this equation. So we have acid-base neutralization here between aluminum hydroxide and sulfuric acid. You end up with these coefficients. And just like when you're baking, like let's say you're making cookies and you decide that you want to cut the recipe in half, you have to cut the quantity of all the ingredients in half. Or if you want to double it, you have to double the quantity of all the ingredients. You can kind of think of that the same way with stoichiometry. So for example, if you've got 1 mole of aluminum hydroxide used and you're trying to figure out how many moles of aluminum sulfate would be produced, look at your balanced chemical equation. To go from 2 moles of aluminum hydroxide to 1 mole, I must have divided by 2. So I'm going to cut all of the coefficients in half and end up with half a mole of aluminum sulfate produced. If I know that I made 2 moles of water, balanced equation shows that I've got 6 moles of water, divide by 3. I take all the coefficients for everything in the equation, divide by 3 to give you 1 mole of sulfuric acid used. Finally, I can make this a little bit more difficult by giving you numbers that you might not be able to work with in your head. We can set up a dimensional analysis to do this. I've got 0.58 moles of aluminum hydroxide. If I go back to the balanced chemical equation, I can see for every 2 moles of aluminum hydroxide, I can produce 6 moles of water. Get my moles of aluminum hydroxide to cancel out, and it leaves me with 1.74 moles of water. See if you can try out this question on your own. The first problem is very similar to the ones we just did. Questions 2 and 3 are going to require some mole conversions as well. As always, start by balancing the chemical equation. We've got the coefficients of 1, 3, and 2. So if you've got 5 moles of hydrogen that you're working with, you can go through the mole conversion, get moles of hydrogen to cancel out. You've got the 2 to 3 ratio, ammonia to hydrogen, and you end up with 3.3 moles of ammonia. Things are more complicated and a little bit more lifelike for question 2. You're probably not going to know how many moles of something you're working with. More often than not, you're going to have masses. So it looks like a lot of work, so let's break it down. Take the number you've been given, 16.2 grams of nitrogen. When in doubt, convert to the mole. We can use the molar mass of nitrogen to get grams of nitrogen to cancel. I'm now in moles of nitrogen. If I look at the balanced chemical equation, for every 1 mole of nitrogen used, I can produce 2 moles of ammonia. This is a really key step as it allows me to go from talking about moles of my reactant to moles of my product. And finally, you're being asked about the mass of ammonia produced, so you need to use molar mass again. Ammonia has a molar mass of roughly 17 grams per mole. Grind through the calculation, you end up with about 19.7 grams of ammonia. Question 3, similar to question number 2. I won't walk through all the steps again. But really make sure that you're paying attention to this conversion factor. This is the step that a lot of students will skip out on. And unless you luck out and everything's in a 1-to-1 ratio, or at least the 2 substances that you're interested in, you're guaranteed to get the question wrong every single time. So make sure that you are using the balanced chemical equation to convert from moles of one substance to another. Just to wrap up, dimensional analysis is really all about making the units work. If you can make the units work, you're going to be able to use this technique to solve all sorts of problems. When we say make the units work, really what we mean is cancel out the units you don't need by getting them in the numerator and in the denominator. So they cancel. And then make sure that the ones that you do need are in the right places. Again, make sure that you've got, for example, with molarity, moles in the numerator and liters in the denominator. Work stepwise and write down the units. For whatever reason, students always seem to fight me on this one. I know it takes a little bit of extra time, but it's going to save you a lot of headache down the road. So take the extra few seconds, make sure that you are not trying to tackle too much at a time, and include the units. Without the units, it's going to be very difficult to keep track of what is what. We're going to use dimensional analysis and not formulas when possible. For example, the MAVA equals MBVB formula that you might remember from Regents chemistry actually hides a lot of the stoichiometry and doesn't work out so well all of the time. So we'll talk about, as those labs come up, how to use dimensional analysis instead of those formulas. And finally, anytime you're working with a stoichiometry problem and you have a balanced chemical equation, make sure that you are going back and looking at the coefficients so that you can convert between products and reactants. Okay, hope you found that helpful, and you'll get a ton of practice with this over the course of this semester.